Good morning, everyone. Morning. It's kind of cool to see everyone in a red shirt here. You know, that's the Wisconsin colors, right? Okay, so today is part 3 and part 4. We're going to be discussing combustion modeling. We're going to have a brief review of chemical kinetics, and we'll talk about HCCI and spark ignition combustion. And then in part 4, we'll discuss aspects of heat transfer and then get into a discussion of emissions, engine emissions, in particular NOx and soot. Any questions before I start up? Feel free to interrupt if you do have questions. So here's some pictures of combustion that you can see on the Engine Research Center website that compare HCCI combustion on the left, spark ignition in the middle, and diesel combustion on the right. So basically, as you know, with diesel combustion, we inject the fuel into the combustion chamber somewhere close to top dead center, followed by compression ignition. Let me see if I can play that again. Of the fuel jets. And you have a very stratified mixture in the combustion chamber with regions that are quite rich, fuel rich, and those tend to produce soot and can be seen in the high illumination or luminosity regions. For spark ignition, we have a spark that's located at the center of the chamber in this example that ignites a homogeneous charge, and you see a flame propagating out toward the boundaries of the domain. And it's a relatively slow combustion process, as you can see, that flame inching forward. And then for HCCI, if you notice there, you'll see the combustion event is really, really fast because in this case, we had a homogeneous mixture that was suitable to ignite spontaneously during the compression stroke. So we discussed yesterday some of the implications of having a fast combustion event, and we'll be talking about that also today. So the other thing I mentioned was that in some cases auto ignition is required, other cases spark ignition is needed to get the combustion process going. For spark ignition engines, one of the parameters that's of key importance is the research octane number. And basically the reason why you're concerned about that is you want to prevent auto ignition of the charge ahead of the flame. So the research octane number is one parameter that is often used to characterize the ignitability of the fuel. And this plot, which I got from Ford, Eric Curtis, shows how the research octane number has changed over the past century, starting at the low compression ratio engines in the early 1900s, compression ratios of 4, very low horsepower per liter. And this is, I guess, World War II around here. They didn't spend much time improving fuels there. But you can see there's this trend towards increasing the research octane number to numbers around 87 or 90 now. And correspondingly, we're able to increase the power output of the engine such that we are now close to 80 or higher horsepower per liter. The other thing you see here is that in order to achieve that, the compression ratio has undergone a consistent increase with time. So this really shows the importance of fuels, because you would not be able to run such a high compression ratio fuel with engine with a fuel with a run of 50 or so, because that charge would ignite during the compression process way before the spark. So the fuels are important, and this is a chart from Oak Ridge National Lab, which kind of describes the advanced combustion regimes that are of interest these days, starting on the left with more or less traditional spark ignition, in this case, a port fuel-injected engine with a spark. These would run with relatively less reactive fuels to prevent auto ignition of the charge. going all the way to diesel on the right here, where you'd like a high reactivity fuel that will auto-ignite pretty much as soon as you have injected the fuel into the combustion chamber. Of course, the difference is here you can run with a homogeneous mixture. In fact, you need to for emissions control, whereas on this side, you have a very stratified charge. The advantage being that you can run very lean mixtures and therefore light loads without having to throttle the engine, which is what you have to do over here. You have to run at partial vacuum at light load. Throttling the engine costs you in pumping work, so that's one of the reasons why spark ignition engines are less efficient than diesel engines. Then in between, we have kind of blends of these technologies. HCCI would be right in the middle, where you have a homogeneous charge that compression ignites at the appropriate time in the cycle. That requires a very special fuel tailored for that particular operating condition. Partially premixed combustion is kind of like SI combustion, except here you inject gasoline into the combustion chamber, maybe having introduced some fuel through port injection as well, or with an early injection to get a more or less homogeneous background. And so here you have equivalence ratio stratification. And then what we'll be talking about later, reactivity controlled compression ignition, where essentially you have one fuel injected in the port, let's say a less reactive fuel like gasoline, and then a more reactive fuel like diesel fuel injected later in the cycle, so that you can benefit from not only stratification of equivalence ratio, but also stratification of reactivity. And this gives you a lot of control over the combustion process, as we will discuss. You require two fuels, though, in this case, and these two fuels, as we'll discuss later, can range from natural gas diesel to gasoline to ethanol. In other words, you can make use of the properties of the fuel to control the reactivity in the combustion chamber and hence the combustion event. So these central sort of concepts fall under the heading here of advanced combustion regimes that we'll be discussing in this course. So let's just talk a little bit more about the basics of spark ignition engines. So we have a spark plug. We ignite a usually homogeneous or premixed charge, gasoline and air. And it's known that these engines operate over wide engine, or can operate over wide ranges of engine speed. How is this possible? Well, the reason is because the flame speed scales with engine speed. And that's because of turbulence. So if it wasn't for turbulence, you would not be able to run a spark ignition engine. All right, well, how is the turbulence generated? We spoke last time about the intake flow process and the jets of air that pass through the intake valves into the combustion chamber. You compress this mixture. Typically, the engine geometry also plays a role. But basically, the idea is you are generating turbulent flows or chaotic or semi-chaotic flows whose kinetic energy scales with the piston speed squared. There are also length scales in turbulence, and an integral length scale, or typical size of the eddies in the combustion chamber, scales with the size of the engine itself. So that's called L piston here. So there's this turbulence that's generated due to gradients in velocity in the combustion chamber also dissipates. And one can calculate an energy dissipation rate, which basically is the kinetic energy divided by a time scale. And that time scale is basically the length scale divided by the velocity scale, giving you a dissipation rate. And then the turbulence itself is enhancing the diffusivity, which is essentially the mixing between either scalars or momentum in the combustion chamber. And this diffusivity then scales with the velocity times the length. If you've studied kinetic theory, you know that we have an equivalent concept when we talk about laminar diffusivities. There, the characteristic velocity is the mean velocity of the molecules, and the length is the mean free path between collisions. So basically, this is a similar concept, but on a much larger scale, turbulent diffusivities being 2 orders of magnitude larger than laminar diffusivities. Okay, so this is the kind of background, and we'll talk a little bit more about turbulence later as well. But how do you model this? Because if you think about it, if the time scale for the combustion depended only on chemistry, there would be no engine speed in the discussion. And that means that you would not be able to run an engine over a wide range of speeds. You'd only be able to run it at one operating point, one operating speed. So what is it that's helping us here? Well, if we look at the species mass fractions, for instance, we've got fuel, we've got oxidizer, we've got products of combustion. The rate of change of species concentration or mass fraction must somehow scale with those time scales. So Professor Bracco and I, many years ago, formulated a model where we basically said that the difference between the local or the instantaneous mass fraction and its equilibrium mass fraction divided by a time scale would be a way you could estimate the rate of change or species conversion rate for any species. So we introduced this idea into our engine models. And it turns out that with this approach, you can actually predict that the flame speed is going to be a function of engine or piston velocity or engine speed. And so the idea here is to go back to the classical early, or I guess 1890 Maillard-Le Chatelier propagating wave analysis, where you have a wave, in this case our flame, propagating into a fuel-air mixture. You can show from the equations that the propagation speed depends on the diffusivity times the rate of consumption of the species or the chemical reaction. If you plug in the numbers that we've discussed here for the diffusivity and for the species conversion rate, you can see that you predict that the flame speed is proportional to the piston velocity. So this is a key aspect of spark ignition engines. And it's one of the things that's actually overlooked in many commercial codes that try to use chemistry to determine the species conversion rate, which is independent of piston speed, right? And the only dependence on piston speed comes through the diffusivity. So they get the result that the flame speed goes as the square root of the piston velocity. So that works maybe if you calibrate your model at one speed, but it falls short at either higher or lower speeds. If we talk about So it depends on which codes you're looking at, but I know some versions of the Converge code had that problem. Also, more recently, Star CD has introduced, as we will talk a little more about this later, but a kind of a blending function that has both a chemistry term and a turbulence term. But certainly in the early versions, they overlooked this fact. And as I'll show you, it's very, very important. Okay, so the turbulent flame velocity, if you're talking about a Formula One car, we're discussing 20,000 revs per minute. If you're talking about a large spark ignition engine, maybe a natural gas engine, maybe you're down at the 100, 200, or 500 RPM range. To be able to cover that whole range of speeds, assuming that the conversion is just chemistry controlled, is just not possible. You have to have something that scales with speed. Okay, so that's kind of a background on spark ignition. Let's look at diesel combustion. It's a little easier to understand, maybe. Here we're injecting our spray into the combustion chamber. We'll be talking more about this tomorrow, how you model that. But what is happening is you're transferring momentum from the injected spray droplets to the environment, or in other words, you're entraining gas into the spray. This gas in the combustion chamber is hot because you've compressed it. That causes the droplets to vaporize, and chemical reactions start. So a kind of an early attempt to try to model this was the Shell ignition model. It was developed in the 70s. This model basically said, I have fuel, indicated here as RH. I have some sort of a reaction that extracts the H to produce a radical species. R star here. And this species builds up and at the same time breaks down to produce branching agents. And a species called Q, which is a labile intermediate species, that builds up to a certain concentration, and when that concentration is reached, you suddenly convert Q, this storage species, into branching agent species, which then undergo very fast reaction to give you ignition. So this is a very early chemistry model that basically consists of just 3 or 4 species, and it kind of gives many of the features that are observed for fuels. So it was a very successful model. However, there's lots of model constants that have to be adjusted for different fuels and so on. So it's not a predictive model. It's more of a qualitative model. The point is, though, that at some location in the combustion chamber, the fuel, air, and temperature conditions are just right for this ignition process to occur. In this case, shown over here, that would occur after some time after the beginning of the injection. So once ignition has occurred, you have essentially a high temperature region that develops and actually envelopes the spray. You now transition to this combustion model that we discussed before, where chemistry is now less important. The thing that's most important is how fast you can mix the fuel and the air. And so using that same idea of a species conversion rate that's driven by the difference between the instantaneous mass fraction and the equilibrium mass fraction, which has the advantage that this goes to 0 when you reach equilibrium. Now the time scale that's relevant is the turbulence time scale generated by this injected jet. You're injecting a very high velocity jet. It is generating turbulence. The length scales are now associated with the size of the jet or the injector nozzle. So this type of modeling was used 10, 20 years ago to make a number of advances, and it's kind of a starting point for discussion. So let's just summarize then for the spark ignition engine. What is it that you want to mix? Well, you have burnt gases and unburnt gases. The unburnt gases are ignited by the burnt gases, and how does that process occur? It occurs through turbulent mixing of the burnt and the unburnt gases. The higher the turbulence, the faster this mixing goes, and therefore the faster the flame speed. And in fact, here's some data showing the ratio of the turbulent flame speed and laminar flame speed as a function of the turbulent characteristic velocity, which would be, for example, the square root of the kinetic energy of the turbulence, and the laminar flame speed. A lot of scatter in the data, but there is a trend, right, that the turbulent flame speed is increasing with laminar flame velocity. So that needs to be somehow recognized in the model as well, right? There is some chemistry component to the turbulent flame speed. It's not just the turbulence characteristic velocities. Looking at the diesel, we just said here that we inject the fuel, we entrain the air. We've seen the time scale is now associated with the injected fuel. And in this case, you can also identify a turbulent flame speed, namely the flame that surrounds this diesel jet. Inside that region, you have fuel and entrained air that are undergoing chemical reaction. Outside the region, you only have air. So there is no place for this flame to propagate. So in this particular case, the turbulent flame speed is actually 0. But you can still think of it as a flame, right? It surrounds this rich fuel-rich region. It's a diffusion flame. Okay, so to summarize the combustion regimes here, the gasoline engine is characterized by spark ignition and subsequent propagation of a flame. In order to have that flame propagate across the combustion chamber in the time available, you need high turbulence. So one characteristic of spark ignition engines, you may notice they have pent roofs, they have all kinds of interesting piston designs. Most of that is really to give you the high turbulence that gives you the high flame speed. On the other hand, though, this leads to high heat losses because the more turbulent a flow, the faster or the more rapid you're going to have heat transfer to the cylinder walls. And so this causes a compromise. There are issues associated with spark ignition if you're running at high load or stoichiometric combustion. You have high temperatures behind a flame. In fact, those high temperatures are required because that high temperature gas is mixing with the unburnt gases ahead of the flame and causing the flame to propagate. So those high temperatures lead to high NOx. Also, if the flame is extinguished because it reaches close to walls that are cooler, you can have unburnt hydrocarbons and CO. But fortunately, the three-way catalyst that was developed in the 70s solves these problems because it is able to essentially reduce the NOx and oxidize the unburnt hydrocarbons, especially for stoichiometric operation. In other words, no excess air in the exhaust. Some of the issues I mentioned is knock. You can have combustion occurring ahead of this propagating flame. You deal with that by maintaining a suitable compression ratio and then choosing a fuel that is less reactive or doesn't undergo spontaneous ignition as readily. In order to control the load, you have these throttling losses that I mentioned, and those generally are responsible for a low thermal efficiency because of the increased pumping work. If you look at a diesel engine, now you have spray combustion. You're injecting the fuel, and I'm talking about the conventional diesel here. You're injecting the fuel into the combustion chamber. Locally, you'll have rich mixtures inside this diesel spray that can lead potentially to soot formation. And in the diffusion flame itself that surrounds this fuel region, you can have high temperatures leading to high NOx. However, because you don't have those throttling losses, you can essentially control the load by injecting just a small amount of fuel for light load and more fuel at high load. You can maintain higher efficiencies, thermal efficiencies. For HCCI, or sometimes you can also discuss premixed charge compression ignition, where you inject diesel fuel early in the cycle. Here you have basically a homogeneous mixture that you compress, and at a certain moment it ignites. We discussed that yesterday a little bit when we looked at this temperature versus crank angle plot here. And we showed that for a less reactive fuel, you have to reach a temperature around 1100 K, like gasoline, and it will ignite spontaneously. For more reactive fuels, like two-stage fuels like a diesel fuel, you have a first-stage combustion with a little bit of exothermicity, followed by compression and then auto-ignition earlier than you would have with the less reactive fuel. And notice I only have one T here because T is uniform, or at least it's assumed to be uniform in the combustion chamber. Whereas in the case of the spark ignition, you have big gradients in temperature across the flame. And in the diesel, you have big gradients in temperature across the diffusion flame location. So the homogeneous charge compression ignition engine is of interest because of this lack of big gradients that could lead to, in the case of rich mixtures, soot formation or higher heat transfer losses. And so it's actually amenable to what's called low temperature combustion, where you mix the gasoline air mixture or the diesel fuel air mixture with recirculated exhaust gases, in this way diluting the mixture rather than throttling for load control. You can use charge dilution. Again, it's chemistry controlled, so the compression ratio is critical, the fuel choice is critical, and as a result you actually have poor load control, because the only thing that determines when combustion occurs here is that combination of fuel and compression ratio. If you dilute the charge, you can get a little bit more control over the combustion using charge dilution. However, if you do it right, you can have low emissions and high thermal efficiencies. So those are the three combustion modes that I want to discuss And today we're going to talk mostly about HCCI and SI combustion, spark ignition combustion. Okay, so let's start with the relatively simple concept of premixed volumetric combustion with chemical kinetics. So this would be of interest, for instance, for HCCI, homogeneous charge compression ignition. If we go to the conservation equations that we showed last time for our system, we have our species conservation equations. We have unsteady term here. We have terms that, convective and diffusion terms that depend on spatial gradients. They're not important if the charge is homogeneous, so we can not look at those for now. This last term here is the source of species due to spray, and there's no spray here, so we don't have to worry about that. So the only thing we're interested in is this term here, which is the rate of change of a particular species with a subscript I here due to combustion or to chemistry. Along with this equation, we are interested in the energy equation. You notice I don't have the momentum equation here because, again, I don't really need that. I have uniform flow, and so I don't have to worry about that equation. In the energy equation, I'm looking at the rate of change of internal energy. I here is the molecule, the energy residing in the molecules plus the kinetic energy. And here I have the heat release due to combustion. All these other terms involve gradients, convection, pressure work term, diffusion, mass diffusion creating energy gradients, and spray and radiation. We don't have to worry about those for now. So we're only interested in the terms inside those circles. And we're going to assume that we can solve those equations in each of the computational cells in our computational domain. Here I'm showing a sector mesh where basically I'm just looking at one piece of a engine. This is the piston down that you see here. And in this case, we're looking at 60 degrees of the 360-degree engine geometry. So sometimes this model is called the well-stirred reactor model because it assumes that the species are mixed inside each computational cell, and all I have to worry about is how their concentrations change with time. So here are my governing equations that I can get by manipulating the energy and species equations for the species mass fraction in terms of the chemical production rates, the mass of species I produced by reaction K. So the indices here, K equals 1 to N reaction, would be the number of reactions that contribute to the species I here. The stoichiometric coefficients are for each reaction. I have reactants and products, and I look at the change in the stoichiometric coefficients, the numbers that multiply the species chemical names or labels in each reaction. And for the reaction rate, as you know from your chemistry classes, we have typically Arrhenius type functions with a forward rate and a backward rate from the law of mass action, all right? So here I have my Arrhenius rate term that involves a pre-exponential, activation energy, and perhaps a temperature exponent. For the backward rate, I use the forward rate divided by the equilibrium constant, which I get from the Gibbs free energy of that particular reaction. Other things that we need to just note here is W is the molecular mass of the species I, rho, of course, the density. And if I take my energy equation, I can rewrite it in this term here, where basically the stuff on the right-hand side is this heat release due to combustion. So I'm assuming that you're more or less familiar with the way that we would construct those type of terms for a chemical reaction. So just to give an example here, let's look at one reaction with methane plus the OH radical reacting with a rate constant K to produce the methyl radical plus water, all right? Here are those equations written in a simpler form. So basically, I would, in order to analyze this equation using the equations on the previous slide, I'd say that the rate of change of concentration of methane is, from the law of mass action, equal to the product of the concentration of the reactants, all right, times the rate constant. And that's going to give me this term here, omega, for methane, which is the mass rate of production, or depletion in this case, of methane, divided by the mass of the species and the density. So if you look, I guess, in Ed Law's textbook here, he can give you numbers for these pre-exponentials and so on. They're listed up here. And we can plot the reaction rate constant as a function of temperature. And that's this black line you see here. So you see that K increases drastically with temperature, as you would expect, all right? Now, along with that, from this equation, methane is being consumed, and so we start with a certain methane concentration, and it's being consumed, in this case, through the H extraction through OH, and eventually we use up all the methane, and so the net reaction rate, or the mass conversion rate, goes to 0, and that's the omega that you see here. So here, omega is 0 because temperatures are low and the rate constant is low. And on this side, the omega is 0 because we've used up all the fuel. So that's just an example of one reaction that would contribute to the depletion of methane. So it's kind of interesting to look at ignition delay, because ignition delay is extremely important when you talk about HCCI combustion. Essentially, you're compressing the charge, and at a certain moment it ignites. What is it that controls that ignition delay? So it turns out that ignition delay is actually, I think, a pretty complex phenomenon to really understand. And just to illustrate that, I'm going to give you an example. If I have a single component system, basically just fuel, let's say, I can show that I can convert these two ordinary differential equations into a prototype ordinary differential equation where U here would represent, for instance, the temperature minus the unburnt gas temperature divided by the burnt gas temperature minus the unburnt gas temperature. So U would be 0 when the temperature is the unburnt gas temperature. That's our initial condition. And it would be 1 when the temperature is the burnt gas temperature. So it goes between 0 and 1. Okay, so here's my equation. Now I need a reaction rate, or a species conversion rate. So I'm going to pick a function here that basically has the same form as we saw for omega on the previous slide. Basically, it's the U, our variable, our dependent variable of interest, to some power m plus 1. Times 1 minus u to power m. This is completely arbitrary, but the good thing is it has the kind of shape that we are interested in, which we can vary depending on what our choice of m is here, to make it look like we saw on the previous slide, say, for methane. We have a parameter beta here, which tells you how fast this is all happening. It has dimensions of inverse time. So when u is 0, this is 0. When u is 1, this is 0. We meet the boundary conditions. So let's try and integrate this equation. So we go to the web, we type it in, and Mathematica comes back, and it shows you that the solution is this hypergeometric function here. And it has a 1 over u in it. And so when you go to try to evaluate the constant of integration, you find that you have to specify an initial value for this dependent variable, which I call u0 here. And so you can expand this hypergeometric function for small values of u, close to u0 here. And you find that the time, the solution depends on time, obviously. It's an ordinary differential equation. And the parameter u0. All right, so if I pick a u0, I can evaluate this expression here. And let's say I'm interested in the time it takes me to go to 5 times u0. I will be able to calculate an ignition delay. And here's my ignition delay. But you see, it depends on u0. So this is something that is really subtle in combustion theory. It's sometimes referred to in Williams's book, he refers to it as the cold boundary difficulty. You basically have to start the system off with something. These are, mathematically kind of unstable situations. You're starting from something close to zero, and it suddenly shoots up exponentially, right? But what is it that you're going to start off with? If you just remove this u here and look at just the ordinary differential equation, you see you have an exponential solution. The initial condition requires that you specify something. And in this case, it's our initial value for u0. Okay, so chemical kinetics, it's one thing to have your rate equations and so on, but you also need to worry about the initial conditions. Okay, so this is, again, a simple example. We're looking at methane oxidation to produce CO2 in water. This is a 15 species, 31 reaction model. And you can see that in order to discuss methane oxidation, you basically have to look pretty far down in the list here to actually find methane. It's over here, reactions 11 and 12, all right? And you see, in order to get stuff going, you need H atoms and OH. So where do they come from? Well, now you have to worry about all of the water reactions, the hydrogen reaction system. And somewhere buried inside these reactions are the reactions that eventually provide you with the H atoms and the OH atoms that participate in the abstraction here to produce the methyl radicals and so on. So once you have those methyl radicals, now you have this whole stream of reaction steps that consume the methyl radicals to produce the formaldehyde. Oops, sorry. The formaldehyde, all right, which is a key intermediate step for methane combustion. The formaldehyde then produces the formal radicals. Formal radicals produce CO. And then finally, we get to the most important reaction in combustion. Norbert Peters would not agree with me. He has another important reaction, but I call this one the most important. CO plus OH gives you CO2 plus H. And that's where a significant amount of the energy is released, all right, in this final step. You'll notice there are other reactions along the way, methylene, methylidyne, and so on, that also contribute to the production of formal radicals and CO and so on. The key thing that I want to point out, though, is that you need something to start off the system, all right? And that really involves these guys, which are, in a sense, catalysts for the reaction system. Okay, so we've seen a relatively small mechanism here with just 15 species. Okay, here's a plot of number of reactions versus number of species from Lou's work here in mechanism reduction. Okay, here's methane. We write down over here. If you want to get to a realistic fuel, it turns out you need a huge number of reactions. And you've obviously seen this before, I'm sure. So, for example, for a C9 species, nonane, for example, or some of the esters, you need on the order of 10,000 reaction steps and reactions in the several hundred. When you get to modeling biodiesel fuels, now you're talking about C18s and so on, and you're really increasing the number of species and number of reactions required to describe that system fully. At least if you look at the elementary reaction systems that are potentially possible involving those species. It turns out that this is just not practical for engine simulations. You would spend most of your time doing the chemistry and you wouldn't be able to look at the more interesting events like the spray and the so on that control the rest of the combustion process. So there's a great interest in reducing the size of these chemical reactions systems. And we typically use as a rule of thumb somewhere around 100 species. And I'll talk a little bit about methods that can be used to reduce huge numbers of species down to a tractable number. The other thing to remember is when you go from 5,000 to 100 species, you've eliminated 4,900 something. What justification do you have? Well, one justification is you're not really interested in those other 4,900. The ones that you're most interested in are the ones that are, for example, legislated emissions, nitric oxide, some of the aromatic species, and so on. So I think there's a lot of justification for reducing detailed mechanisms just from the point of view of what would you do with all that extra information, especially if it's not really needed. Okay, so what we'd like to be able to do is generate reaction mechanisms that are capable of predicting order ignition time accurately and essentially contain the information necessary for you to make predictions of the important pollutants that you are going to be monitoring. Okay, so this just gives a little bit of a review. I'm going to go through this very quickly of hydrocarbon chemical kinetics, because if we're going to talk about reducing a detailed mechanism down in size, we need to make sure that we don't lose some of the essential physics. I already showed you that the Shell model that was introduced in the 70s had a lot of the physics that's needed to describe ignition of hydrocarbon fuels. That was with only 3 species, all right? Anyway, so it's well understood that you start with your hydrocarbon molecule, extract an H to produce a radical species, and then there are these 2 paths. There's the olefin path here, and there's the RO2 path. The RO2 path is important because it leads to the so-called low temperature combustion and the formation of ketone species, which allow you to build up a pool of species through this low temperature branching process. And that shows up as that first stage ignition that I mentioned earlier, with slightly exothermic reactions that help accelerate the ignition process. So basically, I'm plotting here induction time or ignition delay versus temperature. And you can see that we get an acceleration of the chemistry as a function of temperature due to the formation of these low temperature branching steps. And then at a certain temperature, those steps basically become secondary to this olefin channel and the olefins that are formed here. And we go to the second stage ignition, which basically is controlled by the rate at which the hydrogen peroxide molecules decompose to produce the OHs, which then attack the fuel, like we saw in the methane example, to make the cascade continue. And then you have, as you would expect, faster chemistry as the temperature increases. So this seems counterintuitive here to have this slowdown of the combustion, but this is what's called the low temperature chemistry or 2-stage combustion, or sometimes negative temperature coefficient regions, because you actually have ignition delays increasing with increasing temperature. Just as an example here, looking at propane, just a simple alkane here. So we have, through attack by another species, the radical R star. We've removed one of the H's from this carbon atom here. Along comes an oxygen, and of course we have the formation of the RO2 species. There's isomerization. The O here steals an H from this carbon, producing the QOOH. And then we have additional propagation and branching steps, as we saw on the previous slide, leading to this negative temperature coefficient phenomenon. Slightly exothermic reactions producing more or less stable species. Then we have the high temperature branch, which I mentioned before there, where basically the thermal decomposition is controlled by the production of OH, which then attacks the fuel and leads to these fast second stage reactions. This is a slide that I got from Marco Mel at Sandia that I like, which basically shows an engine situation. Here we're looking at temperature or pressure as a function of crank angle, then below the heat release rate as a function of crank angle. And top dead center is kind of indicated here by the dotted line. So we're compressing this charge, and we reach this blue region where you start to see some heat release. And that's because of these degenerate reactions that we saw there involving the aldehydes and ketones. Then you notice the heat release drops, right? In other words, reactions appear to slow down or even stop. And this is derived from looking at the pressure trace like we discussed yesterday and applying the first law of thermo. You see that the rates slow down significantly. Now we're basically producing these more stable species in the orange region. And then as we further compress, we undergo the second stage or high temperature combustion, the paths shown over here in pink. Okay, so we know that if we go to the Lawrence Livermore website, we can get reaction mechanisms for a variety of fuels that are going to consist of thousands of species. How can we reduce that down to a reasonable number? So there are methods that have been developed, like the DRG method. I'm just going to tell you about a more heuristic approach, which basically involves looking at the reaction steps and determining which ones appear to be controlling the various stages of combustion. So here's an example of the Engine Research Center N-heptane mechanism that we created 10 years ago, where we start out with our N-heptane, and we have, in this case, OH as our attack for the hydrogen extraction, producing eventually the ketone species down here. So reactions 1 and 7 are the ones that really lead to the ignition delay that leads to the first stage combustion. The amount of energy that's released during that process is really governed by the rate at which the ketone decomposes into the aldehydes and so on. And so playing with this reaction, one can actually control or at least monitor the amount of energy released. Then we have reactions 3, 4, and 5, which basically determine the second stage ignition delay. And then finally, the most important reaction in combustion, reaction 6 here, which is your burnout stage. So if you play with the rate constants of just these 7 reactions here, you can control the first stage ignition delay, the second stage ignition delay, and also you have some control over the amount of heat released in the exothermic period, plus the final burnout. So that's starting with the detailed reaction, say from Lawrence Livermore, you get an idea of what those rate constants should look like. And with a small amount of tuning, doesn't require a lot, you can match experimental data. So here we're looking at shock tube data, and also there's rapid compression data. But basically here you have your first stage ignition, the second stage ignition. These are experiments matched with the simulations. And here, these are shock tube data, ignition delay versus 1 over temperature. The 2 lines here corresponding to the second stage ignition delay and the first stage ignition delay. These can be matched relatively well with a fairly small size reaction. In this case, we had 29 species to do in heptane, compared to the several hundred in the Lawrence Livermore mechanism. Another thing that Dr. Ra in our group has used as a tool here is a sensitivity analysis. So here's our ignition delay versus temperature plot. You see at high temperatures we have short ignition delays, and then we have this negative temperature coefficient regime, and then the low temperature combustion. What he does is picks each reaction, like for example here's your for tetradecane, looks at the ketone reaction step and multiplies the rate constant by a factor of 2 or divides it by a factor of 2 and looks at what happens to the ignition delay. And as you can see, at low temperatures, it has quite a big effect. And that's because this reaction is occurring at low temperatures, right? At high temperature, multiplying the rate by a factor of 2 or dividing by 2 doesn't really have any effect. So that sort of tells you the sensitivity range. If you want to match experimental data with this reaction, no point in playing with it out here, you want to play with it in this range, right? So the plot down below shows the sensitivity. Here it's 0 at high temperatures and it's high at low temperatures. The other thing, though, is sometimes you're interested in controlling the shape of this curve. And so he uses what he calls a gradient sensitivity coefficient, where basically you look at the rate of change of ignition delay with temperature and produce this sensitivity coefficient, or gradient sensitivity coefficient, which you can again plot as a function of temperature. And here what he has found is that if this coefficient is positive, you can rotate this curve here counterclockwise. That helps you to match data. If it's negative, you find that it's rotating clockwise. So you can look at each reaction in the system and decide whether it contributes to the shape of the negative temperature coefficient and tune the reaction steps that way. So this just summarizes his combustion and flame paper, where basically we looked at a class of reactions starting from the hydrogen extraction all the way to the ketone reaction steps for 3 temperature ranges, A, B, and C here. In other words, low temperature, high temperature, and the intermediate temperatures. And the arrows, the green arrows, show the sensitivity, whether we can move the curve up and down. The dots that you see here that are filled show that this particular reaction is important in both the A and the B and the C regions, whereas this set of reactions here is only important in the B region. In other words, in the negative temperature coefficient region. And looking at the magnitudes of the gradient sensitivities, you can control the shape of this curve, as I mentioned before. Okay, so that's just a kind of an empirical way of dealing with matching experimental data with a relatively small number of species. And as I said, you start from the Lawrence-Livermore reaction rate constants, and these are relatively small variations that are required. So finally, we have an example here of the primary reference fuel mechanism from the Engine Research Center. This is for N-heptane. We start with the Lawrence-Livermore 560 species reaction, 2,500 reactions. And the isooctane, 857 species, 3,600 reactions. And we boil it down to 41 species, 158 reactions by combining it with our N-heptane mechanism. And here you see ignition delay versus 1 over temperature compared with experimental data. You can see for N-heptane, very good agreement. This is for isooctane. And then for blends of isooctane and heptane. So this mechanism is now widely used in our group, and whenever I refer to the Engine Research Center primary reference fuel mechanism, I'll be talking about this particular mechanism, which you can download from our website if you're interested. Now the next step is to say, all right, well, I want to use realistic fuels, not just primary reference fuels. So what we've done to kind of continue this theme is to do the same thing for a variety of fuels where we have actually an idea that involves separating the physical surrogates of a realistic fuel and the chemistry surrogates. So the physical surrogates we'll be talking more about when we discuss sprays next time. But basically, we represent the classes, the chemical classes, the cycloalkanes, the normal alkanes, the isoalkanes, the aromatics, and other ethers, esters, and so on, as physical, with their true physical properties. And since chemistry is not available for all of those species, for example, at the Lawrence-Livermore website, we represent them using the assumption that the N-alkanes can be represented by either N-heptane or by N-tetradecane, for which mechanisms are available at Lawrence-Livermore. So you can see, for instance, for N-tetradecane, the Livermore mechanism has over 1,000 species. We reduce that down to about 47 species for those heavy normal alkanes. And similarly for the other species like the aromatics, we use toluene. The 1,000 reaction steps here are reduced down to around 200. Then we combine all of these into a mechanism that we call the multi-chem mechanism. And here this has roughly 100 species, 300 something reactions, and allows you to track realistic fuels by specifying the composition of the fuel, the amount of alkanes and cycloalkanes and so on, and using this reduced chemistry to model the chemical kinetics. And just to show some validation of this, here I'm showing propane, N-heptane, isooctane, toluene, methyl cyclohexane, decalan, compared against experimental data shown in the references in yellow here. And this is for 8 surrogate fuels listed here. We also have done this for ethanol, for the methyl decanoates, and for biodiesel fuel modeling, plus a variety of other fuels. Okay, so any questions about this? Yeah.
I'm just curious what the impact of radiation, or like the terms we've ignored,
right,
are in terms of the negative temperature coefficient behavior. If I have T to the 4th, are there measures of emissivity for fuels?
Sure, yeah. So I'm going to try to answer that question in the second part of today's lectures. But it's a very interesting area, and I don't think that it's had as much attention as it deserves. So we'll get back to that in a minute. Yeah. This is ignition delay for chemistry. There's no turbulence here, right? Exactly. So I'm going to talk about SI combustion after this. All right, we're going to talk about this is just for the chemistry. Yeah. Okay. So the last slide here before the break is just to show where we're at. Okay, so we've got these conservation equations, and we've discussed the combustion source terms. But when we use them in a practical engine calculation, they still occupy a huge amount of computer time. So the goal is to try to reduce this computer time significantly. So I'm just going to very briefly, after the break, talk about methods that you can use to speed up the chemistry part of the solution. Even if you have only 100 species, that still takes a huge amount of time compared to that shell model, which had only 3 or 4 species. All right? Okay, so I think we have a break until 10 o'clock.